Okay, so we're in section 3.4 now, and we're going to be talking about another differentiation technique. Just to recap, in one of the previous sections, I talked about how some of our differentiation techniques can be categorized as those concerning general types of functions, and those would be our sum and difference rules, constant multiple rules, product rule, and quotient rule. All of those rules deal with general functions. They don't say anything about the function being an exponential or a polynomial or a trigonometric function or anything like that. It just says if you have a function f of x or functions f and g of x, and they are combined in such a way, then this is how we take a derivative. The rule that we're going to be talking about here is called the chain rule, and it's another one of those general types of differentiation techniques. It's not going to, by itself, it's not going to show us how to take the derivative of some specific type of function that we haven't come up with a rule for yet. It will help us derive some of those specific rules after we've established the chain rule. But in particular, it's going to tell us how to take derivatives of a certain way of combining functions that we have not addressed yet, and that's compositions of functions. Now, I think as you will probably see as you progress through Calculus 1 and even Calculus 2, you're going to start to see that the chain rule is probably the most useful differentiation technique that we have. It's kind of a subjective thing. I'm not going to make that a statement of fact, but from my observation with calculus, the chain rule seems to be of more use overall than everything else we've talked about. So it's really important that you get a good handle on this. So let me give you an example of a function that as of right now, as of section 3.3, we are not able to differentiate. It's sine of x, y equals sine of the square root of x. Now we can take the derivative of sine of x. We talked about that in 3.3, and we can also take the square root, did I say the square root of sine of x? The derivative of sine of x. We know how to do that as of 3.3. And we can also take the derivative of the square root of x because that's just the power rule. That's if we're dealing with each of those functions independently. But this is a composition of two functions, and we haven't talked about how to deal with that. So to see that it's a composition, if I were to call sine of x f of x, and if I were to think of the square root of x as g of x, then this function up here can be rewritten as y equals f of g of x. And so far we have not developed a rule for taking derivatives of composite functions, which is what this is. Okay. Now it turns out that composite functions show up extremely frequently in practice, which is why this is such a useful technique that we're about to talk about. So what we're going to do is see if we can derive some kind of differentiation rule. And that's what we have here, this thing called the chain rule. So let's read through this, see if we understand it, and then we're going to create an argument. And I'm careful to use the word argument instead of proof. I'll explain why in a moment. But something that justifies this. So the chain rule says this: if g is differentiable at x, and if f is differentiable at g of x, then the composite function, which we're going to give its own name, capital F equals f of g of x, that's how you read that, which is defined this way, is differentiable at x, and f prime is given by this. Capital F prime of x equals f prime of g of x times g prime of x. And in Leibniz notation, we could also write that this way. If instead of writing this as f of g of x, if we define g of x to equal u, so assigning it a variable instead of putting it in function notation, then f of g of x can be written as f of u, and this exact same chain rule right here can be written this way: dy dx is equal to dy du times du dx. Now, I kind of like this notation, even though I'm going to be using this one more. The reason I like this notation is because it gives you a way of sort of memorizing the chain rule a little bit more easily. I've said before that in Leibniz notation, we're not supposed to think of these things as fractions. at least not at this point in calculus. But if you were to temporarily just pretend that these are fractions, then this right-hand side, you would see that the du's cancel each other out in this product, leaving me with dy dx, which is equal to dy dx here. So if we pretended that these were fractions and then multiplied, both sides would be equal to each other. It's sort of a way of remembering that. Okay? So but coming back here, because this is the form that I'm actually going to be using in practice, if you want to take a derivative of a composite of two functions, I like to use the terminology inside and outside. So the function that's inside here, this g of x, I'm going to be referring to that simply as inside. The f, I'm going to be referring to that as outside. Now, if you've taken pre-calculus or college algebra, you should have had some practice recognizing from the form of a function which function is the inside and which function is the outside, even if you haven't used that terminology before. So up here, this is sine of square root of x, which indicates that the square root of x is like the inside function. I could even put parentheses around this to make it look a little bit more like what I'm seeing here. So square root of x is inside, sine of x is outside, which is why sine of x is called f, square root of x is called g, and then I have f of g of x. But what the chain rule says is if I have a composite of two functions, f of g of x, then the derivative looks like this. It's the derivative of the outside function evaluated at the inside function times the derivative of the inside function. So notice the g of x here is just g of x, not g prime. This is the original g of x function, okay? And then its derivative makes an appearance out here. So until we start doing some examples, it's probably going to feel a little bit confusing. So let's get through this argument first, and then we'll plug away at a lot of examples. Okay, so this I copied from your book, and you notice it says comments on the proof of the chain rule. So this is not a formal proof. There's a problem with it, which turns out to not actually be a problem in the grand scheme of things, but proving that is more complicated than what we're going to show here. So again, that's probably very confusing. Let's just walk through this, and then I'll point out the issue. So again, we're looking at a composite of two functions, f of g of x, which we have up here. And to simplify the notation so that we can use Leibniz notation, I'm going to let delta u represent the change in u corresponding to a change of delta x in x. And the u that we're referring to here is the one stated here. So u is the name that we're giving to g of x, okay? Now, if you have a change in x, because that's the input for our g of x, that's going to give a corresponding change in u, because that's like the dependent variable here, okay? And that corresponding change would be given by this. We've talked about this sort of expression already. Delta u would be equal to g of x plus delta x minus g of x. Okay. So the corresponding change in y, because remember y again up here is equal to f of u. So even though u is the dependent variable here, it becomes the independent variable in my function f. And remember, that's how composite functions work. If I have f of g of x, then I take an input, plug it into g. The output that I get from g becomes the input for f. So it passes that output along into the function f, and then that produces another output from that. So because we have a change in u occurring here, that will create a change in y, because y depends on u, and that would look like this: f of u plus delta u minus f of u. Now notice it says here it is tempting to write, so let's ignore that for a second. Let's just go with the definition of a derivative and see what happens. dy dx equals the limit as delta x approaches 0 of delta y over delta x. Remember, this is one of the definitions that we've given for the derivative using this delta notation. We just haven't used it in any proofs yet, but we're gonna make an argument with it here. Okay. Now, as I kind of pointed out in the chain rule, this thing actually is a fraction, delta y over delta x, and so it's valid to do something like this. This is equal to delta y over delta u times delta u over delta x, because going backwards, these would cancel each other out, okay? So now that I have a limit of a product, I have a rule that allows me to take the limit into each factor of that product. The limit as delta x goes to 0 of delta y over delta u times the limit as delta x goes to 0 of delta u over delta x, okay? Notice here there's no x appearing anywhere, so we're going to need to make a change of variables in order to turn this thing into a derivative of some kind. Okay, now it says here, note that delta u approaches 0 as delta x approaches 0 because g is continuous. And to see that, we go back to our definition. We showed in a previous section that because g is differentiable, that implies that it's also continuous, and we showed that because it's continuous, that means that this particular expression, g of x plus delta x, will go to g of x as delta x goes to 0. But then I end up with g of x minus g of x, which is 0. That's where this is coming from, okay? And the purpose of that is to be able to change this delta x approaches 0 to a delta u approaches 0, since this would imply this. We need this because we need this thing down here, the thing that is approaching 0 should match what we have in the denominator here in order for this to turn into a derivative, because that is following the definition of our derivative. I have that in both of these cases. So this becomes the derivative of y with respect to u. This becomes the derivative of u with respect to x. And that is what the chain rule says right here. Okay? Now, we said up here, it is tempting to write, and I said that I also said that there will be a mistake that's made in this argument. The mistake that's being made is actually right here. The fact that delta x is approaching 0 in this limit means that delta x is never equal to 0 in that process of approaching 0. And we've talked about that with limits. So that means that this quotient is always defined, right? We're never dividing by 0 here. We're just letting delta x get really, really close to 0 when we take that limit. However, the fact that delta x approaches 0 implies that delta u also approaches 0 does not indicate how delta u is approaching 0. It may happen that delta u is equal to 0 many, many times as delta x approaches 0. So we don't know. We don't have enough information to say that we're not dividing by 0 at any point using this delta u right here. So this expression might not be defined for particular values as delta x approaches 0. Again, I understand that might be a very confusing and difficult argument to wrap your mind around. That's okay. I just want to make that point here. So that is a critical flaw in this argument, but it does not disprove the chain rule. Like I said, there is a much more involved argument for why this chain rule is in fact true, but it's also very, very, well, I already said it, it's very involved. The end of section 3.4 walks through the more formal proof of this. I am not going to cover that rule or that proof here. I don't think it's worth our time to do that. You are welcome to look at it if you want. I will say one thing, however. Even though you can get by in this class, and even calculus 2, without knowing that formal proof, it shows up in a certain way in calculus 3. In calculus 3, when you talk about the multivariable chain rule and you talk about differentials in that class, the idea behind the proof of the chain rule in this section makes a reappearance there. If you take calculus 3 from me, I go back and I cover that proof first here. So yeah, that shouldn't be a concern. But anyways, I've spent enough time talking about that argument. Let's go ahead and take a look at some examples. So let's take the derivative of the function that we wanted to, or that we presented at the beginning of this section, sine of the square root of x. Okay, so again, remember, we defined f of x to equal sine of x and g of x to equal the square root of x. Okay? And going back to my chain rule, what are the ingredients that I need to take a derivative of the form f of g of x? Well, I need the derivative of f, and I need the derivative of g, and then I also need g itself, okay? So we have f and we have g, but we don't have either of their derivatives. So this would give me f prime of x equals cosine of x, because that's what that's what the derivative of sine is. Here we would have g prime of x, which you can use the power rule there. Keeping things in radical form, I would have 1 over 2 root x. Okay? So now how do we take the derivative? Well, the derivative of sine of x, it's very sloppy, is the same thing as saying that I want to take the derivative of f of g of x, because this should be a square root. The derivative of sine of the square root of x should be the same thing as d dx of f of g of x based on how I defined f and g here. My chain rule says that this is equal to f prime of g of x times g prime of x. Now I go over here and I find all of those components and put them into this form of the chain rule. F prime of g of x. F prime is cosine of x, g of x is the square root of x. So I want f prime of g of x, cosine of square root of x, times g prime of x, which we have here, 1 over 2 root x. Or I would prefer to write that this way, cosine of root x over 2 root x. Okay? That's the chain rule. So I went through the process of labeling things f and g and then finding their derivatives, and I'm going to do that one more time, but then for the remaining examples, I'm not going to do that anymore. And the reason for that is because in the process of, or in using the chain rule, you do not want to spend this much time on it. You want to be able to do this relatively quickly. And once you've done the chain rule enough times, you will see this derivative without having to do all of this stuff. But this is just for these first couple of examples as we're getting used to things. Okay, here's another example. I would like to find the derivative of this, y equals quantity 2x plus 5 to the 9th power. You do not need the chain rule to do this, but the chain rule will make your life vastly easier if you do. The reason you don't necessarily need the chain rule is because if I were to take this binomial, 2x plus 5, and expand it to the 9th power using the binomial rule or just basic multiplication of binomials, then, I said binomial theorem, not binomial rule. I could expand this out into a big 9th degree polynomial. And then I could differentiate that term by term using my power rule. That would take a very long time because this is a relatively large power, and that is a lot of work to do just to expand that thing. Fortunately, the chain rule allows us to get away without expanding it at all. So in this case, we want to look at this as a composite function. What is the inside and what is the outside? Well, I have a 2x plus 5 in parentheses, indicating that that would be my inside. And then I have a 9th power on the outside. So that means it would make sense to say that f of x is x to the 9th power, and g of x is equal to 2x plus 5. That way, you can see that this is f of g of x. This is being plugged in for the x here. Oops, excuse me. Okay, so now, following the pattern as above, I need f prime and g prime. F prime of x is 9x to the 8th power, using my power rule. G prime of x is just 2. It's the constant function 2. So now, if I want the derivative of this, y prime, according to my chain rule, it would be f prime of g of x times g prime of x. And let's put the pieces together. F prime of g of x is what I get from plugging this expression into f prime of x here. 9 times 2x plus 5 to the power of 8. So that takes care of this right here. times g prime of x, which is equal to 2 times 2. Of course, I can multiply the 9 and the 2 together to get a simplified version of that, 2x plus 5 to the 8th power. Vastly, vastly simpler than expanding this out first and trying to do the product or the power rule for all of those terms that would pop out of that. That would be 10 terms in total for this polynomial, and just expanding that alone is a time-consuming process. Interestingly enough, if I were to have done that, I would have, after differentiating, I would still have this big expanded polynomial. But whatever the result of that would have been, it would have factored to this. And it would have been very difficult to see that it factors to this. So not only does the chain rule make this process take much less time, it also spits out a factored version of the polynomial that you would have gotten in the first place, which is generally much more preferable. So the chain rule is vastly superior to the other approach here. I'm going to go ahead and stop this first video here, and we'll keep doing examples in the next.